Hello, my name is Dylan Holzman and I'm a senior mechanical engineering major here at the University of Maryland. The following video is a culmination of a semester-long project for the class ENME435, Remote Sensing and Instrumentation. For this class, we were tasked with designing a LiDAR sensor to map a target on campus. We do this using the Raspberry Pi, Python, OpenCV, and other components. I hope you enjoy the video and thanks for watching. My target of interest is the fountain at the Garden of Reflection and Remembrance. I chose this location as I often visited this spot to relax, do homework, or catch up with friends. Here's the field deployable LiDAR sensor we've created. We started with a 3D printed board to use as a mount, and that is the orange part at the bottom. And then we have three main components. We have our Raspberry Pi with the camera module. This is going to capture images and process them. And then we have our power supply, which is either our battery pack or the Arduino. And then we have our laser here. And when this is plugged in, our battery pack supplies power to our laser, and this is held rigidly in place with a set screw. So here we're calibrating the laser to the camera, and we want to make sure that they're in line and vertical for when we scan our target. The camera is held rigidly in place with rubber bands, and then the laser is held in place with a set screw. And then we can see with our Python code, the lines match up, so it is calibrated. So now we're calibrating the LiDAR from a single beam to a line laser, and we do this by measuring our distance from the wall with a tape measure, and then we take the images using the Raspberry Pi, and we'll do this from 0 to 10 feet. Here we are mapping our target, which is the fountain ahead. We have the field deployable LiDAR system with the laser at the bottom and our Raspberry Pi up top. And as you can see, it shows on the fountain, and then we're taking pictures with the code. So now we're out shooting our target from a different angle. Previously, we were over there where the tape measure is, and now we are 90 degrees away. We have our camera module, our laser, and we're running the code to take the images. Here we are on the last side of our scan for our target. We're gonna run into some problems later because the ground is not perfectly flat. As you can see, we're in a mulch bed. However, if I go on the other side of this retaining wall, it would be flat, but we'd be too close to the fountain to get a good image of it. Here's how our data collection code works. With the laser pointed at the top of our target, we start by inputting an IMU angle. We do this by resting a phone on top of the LiDAR setup and using a level app. We can tell the angle of the camera with respect to the horizontal. Then, using Raspberry still, we take a long exposure photo. Since it's dark out, this long exposure helps with the clarity of the image. After our image is saved, we rotate the camera downwards and repeat the process. As you can see, all of the photos are labeled with the IMU angle. And as we increase our angle, the laser moves down on our target. So after taking all of our pictures for our scan, we use Color Picker to filter the H, S, and V values. As you can see here, we have a good representation of what we want to display from our image. And then after that, we take all of our pictures, which are in this Cloud One folder, as you can see. And then we run our data generation code here in the terminal. And as you can see, this loaded in every picture and extracted the data from it. And then here is our scan. So you can see here is the curvature of the fountain, and then back here is our retaining wall. We'll put this into MATLAB and we'll get a better image later. After we took our images with our Raspberry Pi and ran the code, we're left with text files of the coordinate points from our laser lines. And since we took images from 4 sides, we have 4 different text files with different coordinate points. So we go to MATLAB and we run this code that plots these points and puts them on a cloud map. And as you can see, once this code runs, it's going to be messy and there's points that we aren't going to want to use in our final product. So as you can see, all these points off here to the right and the points in the front, and then there's an extraneous point up there at the top. All of these are going to be filtered out with our next code. You can see back here, this is the retaining wall that was behind the front scan. So after a bit of work on MATLAB and running through different filters and transforming the data and filtering out just different points that we don't need, the fountain ends up looking pretty good, as you can see here. And it's upside down, but let me rotate that. So now you can see we have all four sides of our fountain and we have the lines going across the top. And then we're going to put this into MeshLab and create a mesh of our target. Now that we've completed the point cloud in MATLAB, we can save a text file of all the points that we're going to use for this mesh here. So we're going to start by importing that file. And as you can see, this is exactly what we had over on MATLAB. So now we're going to add a ball pivoting surface reconstruction with a value of 10. Next, we're going to add an alpha wrap with a value of 0.09. And this closes all of our lines and creates the outline to our fountain. But as you can see, the edges are rough and we need to smooth this down. So we're going to use a Taubman smooth with a step size of 10. And as you can see, it's a pretty good representation of the fountain. In the future, we should take better pictures and take more pictures so that these holes aren't so big and the image comes out a little bit clearer with better defined edges. But other than that, I think it's a pretty good representation of our fountain. And here's the final 3D printed model of our fountain. Thanks for watching.